Good evening to everyone. In continuity of the previous session, we will be discussing about how to derive the maximum efficiency relation for any of a reaction turbine. Till now, we have derived an expressions for work done, power developed, blade height, degree of reaction, and if I want to represent this blade height and the mass flow rate in terms of diameter and in terms of K, where K is a constant and it is a ratio of a blade height to the diameter of a bead. And we have derived the mass flow rate for both the cases where the nozzle is having a total flow of a complete coverage of around full. If it is a full, we consider the entire circumference, and it is not a full, then we consider only the number of blades covered by nozzle in terms of again the pitch, the blade in given in terms of meters. Now today's session, now in continuity of the previous session, that is the reason why I'm trying to recap the things that we have learned in the previous sessions, right? And now in continuity of that, now we are going to derive the relations for the conditions of the maximum efficiency of a reaction turbine. What are the conditions? Condition for maximum efficiency of a reaction turbine. In the previous session, similar way we have derived the relation for the maximum efficiency of an impulse turbine as well, right? And now here work done per kg of steam equals to VW1 plus VW2 multiplied by U, right? Per kg. That is the reason I am not writing the value of m here, right? Now, if I correlate it with the velocity diagram, I'll tell you how to draw the velocity diagram for this reaction turbine in the next sessions, right? V1 cos alpha plus VW2 is VR2. V suffix R2 cos pi minus U whole multiplied by U. Is this clear now? Now, for for any of the reaction turbine, what is the condition we have in the starting sessions of this reaction turbine? What is the condition we have taken? Alpha equals to pi and V1 equals to VR2. Therefore, work done is given in terms of 2 times of V1 cos alpha minus U whole multiplied by U, right? If I want to take V1 as the common, right? Can I take the V1 as common? Yes. V1. If I take V1, it will be 2 cos alpha minus U by V1. If I take V1 square as common, 2 cos alpha by V1 minus U by V1 square in terms of U. Yes, ma'am? Is this clear? Now, still I can simplify the relation. Work done equals to V1 square multiplied by 2 into U into cos alpha divided by V1 minus U square divided by V1 square. Yes, I simply multiplied bought this u which is outside and I've kept inside the brackets. I've multiplied with all the terms right here. Now it is nothing but v1 square into 2 multiplied by r into cos alpha minus r square. It's not, don't get confused between this r and v. It looks, I'm writing in the same way. I'll correct it. R minus R. Is this clear now? Yes. Now here we'll write a relation for a blade speed ratio. U by V1. Right? Always remember this relation for work done. Now we'll write the relation for the total energy supply. Total energy supply equals to energy supply to fixed blade plus energy supply to moving blade. How the energy is being supplied in form of kinetic energy, right? Now we will write the relations for how the energy is being supplied to the fixed blade and how the energy is being supplied to the moving blade, right? V1 square divided by 2 plus VR2 square minus VR1 square divided by 2. But I know that since VR2 equals to V1 and VR1 equals to V2, where we have seen in Pascal's reaction turbine, we have seen that. When can we say that is a Pascal's reaction turbine? When both the moving blades and the fixed blades are symmetrical, right ma? In that reaction turbine we have seen this condition. With this condition only we are going to derive the relations to have the maximum efficiency, right? Therefore, total energy supplied equals to V1 square by 2 plus V1 square minus V2 square divided by 2. I have replaced with VR2 is been replaced by VR1 and VR1 is replaced with V2, right? And now can I simplify this? Yes. If I simplify this, what would be the relation? 2V1 square minus V2 square divided by 2. Now, how to find the value of VR1 square? VR1 square equals to VW1 minus U whole square plus VF1 square. You can recollect the things what we have done in the impulse start with the same expression, same relations, same derivations, right? VR1 equals to square root of V1 cos alpha minus U whole square plus V1 square sine square alpha, right? Am I clear? Similarly, it is nothing but V2, right? VR1 is nothing but V2. Square root of V1 cos alpha minus U whole square plus V1 square sine square alpha. Still further, if I simplify it, expand it, I'll get a relation as V1 square plus U square minus 2U V1 cos alpha. And these are the values of V2 and VR1. Right? Now, since the total energy supply equals to 2 times of V1 square minus V1 square plus U square minus 2U V1 cos square alpha divided by 2. Still further, if I simplify it, it will be V1 square minus U square plus 2U V1 cos square alpha divided by 2. Still, take out V1 square by 2 common. First term will become 1 minus U by V1 whole square plus 2U by V1 cos alpha. Right? This is cos alpha. And further, if I simplify it, it will be in terms of V1 square divided by 2 into 1 minus rho square plus 2 rho cos alpha. This is the second expression that you have to attain the maximum efficiency. It is total energy supply. Right? This is the expression. Right now? Now, if I want to find out the blade efficiency, or we have another name called as a diagram efficiency as well. Diagram efficiency, or we can call it as blade efficiency. Right? Now let's see how it is given. In the previous relation for the impulse turbine, it is the same as that ratio of work done to that of the energy supplied. That is the reason till now we have calculated the relation for energy supplied, right? It is nothing but V1 square into 2 rho cos alpha minus rho square divided by V1 square by 2 multiplied by 1 minus rho square plus 2 rho cos alpha. Can I cancel out V1 square, V1 square? Yes. Blade efficiency equals to 2 times of 2 rho cos alpha minus rho square divided by 1 minus rho square plus 2 rho cos alpha. Clear, huh? This is the relation for blade efficiency. Let this be third equation. This is the third expression. Right? Just recollect the topics what we have discussed now. After this, we will discuss about efficiency when it will be maximum, under which condition we will discuss, right? Or if not, just now, now also we can say that efficiency will be maximum whenever the denominator is minimum. right? The condition will be the same.